All right, so the last time we talked about how the integral lines of the gradient flow of a Morse function, um, partition up it's the manifold in some sense. Okay, so now we're going to look at and in particular they either start or end. It's like at a critical point. So and of course this draws upon ideas from dynamical systems theory. And in particular, the next obvious thing to look at then are the stable and unstable manifolds of these critical points. So that's what we'll discuss right now. So stable and unstable manifolds. Okay, so the stable manifold of a critical point U of f, right, is the point itself together with all regular points whose integral lines have U as the destination, right? So they end at U, okay? And then we can also have the notion of an unstable manifold. So the reason why it's called a stable manifold is because if you think again of moving forward in time, right, then the set of regular points which end at U are basically the set of points where if you start there and you follow the gradient flow, you'll eventually reach U, right? So these are the set of points which approach U. It's like a limit to U. It's like in sort of the limit of positive time, okay? And the unstable manifold is what you expect is the reverse of that, right? So these are the ones which sort of, if you're close to the critical point but you're not actually at it, it's like then they sort of diverge away from get critical point. Or another way to sort of think about it is that they approach the critical point as you go in negative time, right? Okay, so symmetrically then, right, the unstable manifold of U is the point itself, right, together with all regular points whose integral lines start at U. Sort of originate at U. Okay, so I can write S for stable. So stable manifold of U is set U unioned with the set of points in the manifold with the property that the destination of gamma x, right, is equal to U. Okay, and then the unstable manifold of the point U is U union x in the manifold with the property that the origin of the integral line which goes through x, right, is U. Okay, so as before, the function increases along integral lines, right? So that means that f of u, right, is going to be greater than equal to f of x for all x which are in the stable manifold of u, right? And then conversely, f of u is going to be less than equal to f of x for all x which are in the unstable manifold of u. Okay. And then if you recall, it's like we had sort of talked about the index, it's like of a stable manifold. Sorry, the index of a critical point. Okay, and then you can ask yourself, you know, for these sets, what these sets, yeah, so these sets, what they look like in some sense. It's like geometrically. Okay. Okay, so yeah, so before I do that, it's like because of these conditions, we say that S of u is also sometimes referred to as the descending manifold. Okay, and of course this is really sort of just in the case of the dynamical system. It's like which comes from the gradient flow. It's like of a Morse function, right? So in general, this idea of ascending and descending, it's like doesn't make sense. It's like for a generic sort of dynamical system. It's like, but if the dynamical system comes from the gradient flow, then you sometimes have these terms instead. Okay, so referred to as the ascending manifold. Okay, all right. All right, so now it's like, let's say a little bit about what these things look like. Okay. So if the dimension of M is D and U is a critical point with index Q, right? If you recall, it's like the index has to do with the number of essentially negative directions at that critical point. It's like, and in 2 dimensions, it can be used to classify critical points into minima, maxima, and saddle points, right? So anyway, so as you might expect, then it's like the index of the critical point is going to tell you something about the dimension of these stable and unstable manifolds. Okay. So, all right, so if you have, excuse me, if you have critical point, it's like with index Q, then there's a Q minus 1 sphere of directions, right, along which the integral lines approach U. Okay, and again, you can see this because it's like the index tells you the number of sort of directions in which the Morse function is decreasing in essence, right? So so if you have this gradient flow, it's like where the Morse function increases along the gradient lines. These are the set of directions, it's like where you expect the integral curves to then approach the critical point U. Okay, then, all right, so there's a set of these q minus 1 spheres. Sorry, there's a q minus 1 sphere of directions. It's like, and then if you sort of look at essentially the, it's like the sort of essentially the stable manifold, right, which is sort of the union. It's like of these directions together with, it's like with U itself, right, then you have a ball of dimension Q, right? So then basically, S of U, right, is an open ball of dimension Q. Well, I mean, and yeah, okay, and it is homeomorphic to RQ, and is immersed in the manifold M. Okay. So you might ask why it's only immersed as opposed to embedded, right? So it's not embedded because distant points in RQ, right, can be mapped to arbitrarily close points in M. Okay. All right. And in a sense, it's like, when we talked about what happens at critical points, it's like when you sort of, it's like do this gluing, it's like of a ball of dimension Q, right? When you sort of just go past the critical point and you, see how the topology, it's like of the level sets, the sublevel sets change, right? This is related to this idea here. Okay, and in fact, if you recall, it's like we alluded to the idea that you can prove all of this, right, by looking at, it's like the gradient flow of the Morse function. Okay, all right. Okay, so anyway, so you can, you have this kind of gluing phenomena, all right. Yes. Okay. So now you're more or less in a position to start talking about, what kind of functions you want, so that you have some notion of genericity. Okay. And the basic idea, if you will, is that in a generic dynamical system, then these stable and unstable manifolds, it's like they don't, it's like they sort of intersect transversally, right? So more or less, it's like what that means is that if you look at the linearization of those two spaces, right, then they are sort of complementary. Right? The only intersection it's like of the linearizations of the stable and unstable manifolds are at the origin itself, which more or less corresponds to the point U. Okay, and so that's kind of a generic situation, and so basically what we're going to look at then are Morse functions whose gradient flows give you stable and unstable manifolds. It's like which have this generic property that the stable and unstable manifolds are transversal. Okay, all right. So let me just stop here for now.